So we've talked about the concept of work. We have seen how to compute the work done by some of the standard well-known forces like gravity, linear elastic forces, as well as friction. But in the work energy approach, we have not talked about what the concept of energy is. So we will discuss first the concept of kinetic energy. So what is kinetic energy? Kinetic energy in a system, whether it's a particle or a rigid body, is due to its motion. So kinetic energy, I'll write it as KE. KE is due to motion. Okay, so if something is translating, so if you have an object that's translating, whether it's doing a rectilinear translation like in this case, or it is doing a curvilinear translation where the orientation does not change. So let's say this is the curvilinear translation. In either of the two cases, the kinetic energy due to translation, I'll call it KE translation, is defined as 1/2 mass times the speed squared. So you have to know the mass of the particle or the object, and you have to know its speed. And of course, if the speed is changing, then kinetic energy from time to time would be changing. But at any given instant, kinetic energy of a translating object is given as 1/2 mv squared. Okay, so that's the simple part. So if you can identify if something is translating or not, and if you know its mass and speed, you can find those. Okay, so example, let's say I have a block that's of mass 1 kilogram, and at any given instant its velocity is 2 meters per second, and I ask you what is kinetic energy, then you can easily write that as 1/2 mv square, and that's 1/2 times 1 times 4, so that will be 2 joules. Okay, so that's the kinetic energy, right? Now, what about non-translating objects? So this is kinetic energy due to translation. So let's say I have a disk, okay, and disk is rotating about its center of mass about 0.0 with certain angular velocity omega, or angular speed omega. Kinetic energy of a rotating object, a purely rotating object, so this is a pure rotation because this is rotating about a fixed point, is given as 1/2 centroidal mass moment of inertia times omega squared. That's the formula for kinetic energy of a rotating object. So if you have a rotating object and it's rotating about a center of mass, then you can write its kinetic energy as 1/2 Ig omega squared. Now, if let's say a rigid body is rotating about a point other than centroidal mass moment of inertia, even then you have a similar expression. So if let's say you have an object and it is actually rotating about a point O, which is not necessarily the center of mass. So here O was same as G, and this is how it is rotating about this point. Then also you can write kinetic energy of rotation as 1/2 I about O. So instead of I being about G, now I is about O times omega squared. Okay, so that's another formula. But this is not a formula that you need to really remember for this class for now. Just keep that in mind that you could write that as well. Now, what about general planar motion? So if you have a general planar motion, then kinetic energy is defined as kinetic energy due to translation plus kinetic energy due to rotation. So those two energies basically add together, and kinetic energy is a scalar quantity, so that you can add them together. So if let's say I have a wheel, okay, let me first finish writing this. So this is 1/2 mv g squared plus 1/2 Ig omega squared. Okay, so that will always be valid. So V would become velocity of center of mass for a rigid body. So if I have a wheel that's rolling without slipping, so rolling without slipping, okay, and let's say we know the velocity of center of mass as I don't know, V0, okay, and its radius is given to you as r, then the question is, what is kinetic energy? Now, kinetic energy of this wheel, let me call it kinetic energy of the wheel, is equal to 1/2 m times velocity of center of mass squared plus 1/2 Ig omega squared. Okay, so we know that with Vg over here, velocity of center of mass is same as velocity of O, because that's center of mass that's given to us. And we also know that Vg is equal to r times omega, right? The angular speed. If it is rolling without slipping, we have seen this relationship to be true. So that gives us omega equal to V0 over r. So the kinetic energy would be 1/2 m V0 squared plus 1/2 Ig. We will model it as a disk. So that would be mr squared over 2 times omega squared, which is V0 squared over r squared. So r squared cancels. So we get what? 1/2 mv0 square plus 1 half. So this becomes actually 1 over 4 mv0 square. So this would be 3 over 4 mv0 square. And that's the kinetic energy of a disk or a wheel that's rolling without slipping, right? So notice that if you model this as a particle, then you would not have this term, right? So you have two terms over here. One is due to the rotation, the other is due to translation. So if you model this wheel as a particle, then there will be no rotation, in which case you'll only get 1 half mv square. But if you model as a true rigid body where you allow for rotation to happen, that will be 3/4, right? So in this case, the kinetic energy is of course definitely higher than it would be if you model it just as a translating object.